So a square coil wire with sides of 0.025 contains 1,000 loops, has 0.6 Tesla magnet, removed completely in 0.1 seconds. What's the EMF? So you have this kind of square loop of wire, and I'm not going to draw all the loops, obviously. That would take forever, and I'm not very good at it anyway. So we have that, and then we have some amount of field that's removed. So the field is going through like this. Okay, and that's from some magnet we have. And we're removing the magnet. We're pulling it out. Okay, so I know that the length of one of the sides of the squares is 0.025. And the first thing I do before I do anything else is I turn that into an area. So this is a square coil of wire. So the area of a square is length squared. So to find the area, I'm just going to do 0.025 squared. And that's going to be, I feel like I hit the wrong button. Yep, I did. 0.000625. Okay? So that gives you the area. Then it tells me that there's 1,000 loops. There's no unit for loops, it's just the number. And it has 0.6 Teslas removed. So we need to find the change in the field, not just the value for the field. So the change is, what does the value go to and what did it come from? So whenever you find change in anything is final minus initial. So it's what's the field at the end minus what's the field at the beginning. Well, if it says it's removed completely, that means the field at the end is 0. And since the field at the beginning was 0.6, the change in field is negative 0.6. And the negative is important for figuring out the directions here. So be careful. I noticed most people just had 0.6. That's an easy mistake to make. So just be careful with that. Okay, and then the time it takes to do this is 0.1 seconds. So then we're ready to set up. So the equation is EMF equals negative N, which is 1,000, times A, which was 0.000625. You can certainly do scientific notation, but I know that makes people sad a lot of times. And that's equal to change in magnetic field, so negative 0.6 divided by the time, which is 0.1. And I'll leave you to solve the rest of the math out there, but that's the idea. You're going to end up with a positive answer. Okay? When you get a positive answer, that's how you figure out the direction. It's the easy. I shouldn't say that's how you figure it out. It's the easiest way to figure out the direction. So we know that it is always going to be in the opposite direction is the induced field. So positive means in, negative means out. So when I get a positive answer for the EMF, that means the direction for the induced field is in. And then I can do my right-hand rule to figure out, okay, if it's in, what direction is the current? So I think of it like this. Okay, the induced field is in. Okay, there's my field going through it. I know that first right-hand rule, my thumb is the current. My fingers wrap in the direction of the field. So if the field wraps around this way, then my thumb is in the direction of the current, and my thumb is pointing clockwise. So that's my answer here. It's worth double-checking your answer for B and asking yourself, okay, the induced field is always opposite of what's being done. So I'm removing the magnet. That's a flux out. The change in the field is out. So the induced should be opposite of that, which is going to be in. So that's kind of how I think through it and how we work on the directions and that sort of thing. All right. You can put that off to the side. And what